sorry. Colin, are you here? Do you? Okay. Updating event Mobi. Yay. Okay, great. Okay, Lourdes just a very quick set. So I'll thank you so much for those who are joining us on event Mobi. Sorry for this small hiccup with the video. So I want to do the introduction once again. I'm sorry, but I just wanted to remind you that there is a lag in between what we see as this on Zoom and what you see on Event Mobi platform. So please feel free to submit your questions during the talk, and you don't feel obligated to wait until the end. And again, I wanted to introduce Lourdes Aquino from Universidad Nacional de Mexico. Lourdes, go ahead now. Now we can start.
Okay, hi everyone. Today I'm going to talk about my research. It's about modulation of the urban heat island by synoptic patterns and their intensification with heat waves over Mexico Basin. Okay, the presentation is aligned by background, methods, results, highlights, and future work. About the principal orographic characteristics, the Mexico City is over a plateau, and this plateau is over 2.2 kilometers above sea level, and over this plateau is the basin. And over the basin, inside the basin, is the Mexico City or the Valley of Mexico. And in a view from the northeast from the valley, as you can see in the picture of the right, there are mountains in the east, west, and southeast part, and in the southeast part of the valley, the mountains start to decrease the altitude and then create or generate a kind of bridge or gap between the Valley of Mexico and Morelos Valley, and this valley is at 1 kilometer below to Valley of Mexico, and then this configuration of orographic characteristics leave the downslope upslope winds between the mountains, and also a low level jet between Mexico Valley and Morelos Valley. Okay, other important thing, it's Mexico is home one of the mega cities in the world, and Mexico City has 22 million inhabitants, and this is expansion of urbanization changed drastically the land use land cover of the valley from natural areas to urban areas. In 1930, the urban heat island was near to 6 degrees, and the city was in the core of the valley. But after 5 decades, in 1980, the urban heat island changed drastically and increased 15 degrees this phenomenon. But this is because the expansion of the urbanization increased over the mountains, and then this create other factors. For example, the altitude in the urban heat island effect. That is the difference between the urban region with the surrounding areas. And now, the urban heat island changed the characteristics, the intensity, seasonal to seasonal, and also day by day. And these characteristics day by day are influenced by synoptic conditions. When we evaluate heat wave extremes, we also need to consider the heat waves. And these heat waves are principally modulating by the synoptic scale. And also now the objective of this work is to evaluate what synoptic pattern get the intensification of both phenomena, the urban heat island and the heat wave. For a specific climatology season, climatology period from 1990 to 2019. For this, we only focused on the dry season because in the precipitation or wet season, the precipitation acts like a cooler mechanism, and then this phenomenon is less intense than the dry season. About the data, we use surface data distributed in all the valley. And this is, and those stations have to get a classification to reduce the error if the station were in the mountains. And then also use ERA 5 analysis to numerical experiments. With the station, we divide in split in 4 sectors: is the north, east, south, and the urban region, and we don't consider it a sector in the west part because in the west is near to the mountains. To get the urban heat island intensity, we get the difference between the urban region minus the rural sector, for example, the north, east, south. And to get the heat waves events, we use the maximum surface temperature considered at the threshold, the 90 percentile, when this threshold keep for 3 consecutive days or more. About the numerical experiments, we use numerical experiments with high resolution from 19 kilometers to 2 kilometers in 3 domains, and for the analysis only use the innermost domain. Also, to get the effect for the urban expansion, we use 3 land use land cover scenarios. In the first one, we don't have urbanization. The second one is the past condition, represent 2017, and the last of the final experiment represent a projection of urbanization to 2016. And the boundaries of the initialization of the model represent a case study for May 1998. Okay, to get a classification, we use the classification proposed for these authors, Diaz Esteban et al., and they get with ERA 5 reanalysis using wind fields at 500 hectopascals, 7 water types. And with these water types, we analyze the intensification of both phenomena. Okay. Also, it's important mentioned that the urban heat island it's keep on all diurnal cycle, but in the case the urban cool island, the phenomenon is a specific characteristic when the urbanization start to interact with local mountain circulation. In the specific case study, we get an intensity near to 1 degree, but in the climatology is very slight. It's 0.25 degrees. And about the heat waves, the frequency has increased slightly by 0.7 heat waves per decade, but the intensity and the duration has decreased by 0.1 and 0.8. But we only consider this period, from 1990 to 2019. Okay. Also, in this picture, I show you the water types are in the rows, and the frequency of the heat waves are for every month are the columns, and the first 4 columns are for the dry cold subseason, and the other columns are for dry warm season. And then we can see that in the first water types, it's more frequency, is a more frequent that the heat wave presents in that period. About the intensity of the urban heat island, also represent the water types in the rows. In the first column is all the phenomena, all the cases considered urban heat island and heat waves, and the second column represent only heat wave intensity. and the difference, we get the heat wave effect. And then we can see that in the water types 2, 3, 4, principally in the dry warm season, there are a heating effect for both phenomena. About the urban cool island, that is new characteristic in the diurnal cycle. Also, we can see in the dry warm subseason that in the water type 3, 4, and 5, there are a warming or heating for the interaction of both phenomena, the urban heat island and the heat wave. Okay, about the winds, the intensity of winds for the urban heat island, that it represents the morning observation. Also, we check that the intensity of the winds was reduced, and in the afternoon, the winds also, it's associated with light winds or cold winds. Then it's a signal that the heat wave limited the ventilation and reduced the circulation inside the valley, inside the basin, sorry. About the advection, we get the components of the advection in the zonal and meridional axis, and the third column represent the transport in the vertical. And then in the first three water types, we can see that there are a more warm advection from southeast that enter to the valley and then keep inside of the valley. And in the afternoon, the circulation keep anticyclonic circulation. And then in the afternoon, there are also a warm advection, but this advection come from to the north. And about the transport in the vertical, this heating inside the basin produce more increase of the planetary boundary layer. Okay, if we also analyze a specific event, a strong event of heat wave for May 1998, and in this graphic we can see the days and the evolution of the temperature, and specific in the more or higher temperature was in the days in between 8 and 12 of May, and we get the higher temperature. And when the threshold was near to 28, but when we get the heat index like comfort thermal index, we see that the temperature it's near to 32 degrees, and it represents a fatigue and cramps possible with prolonged exposure and activity. About
1 minute.
Okay, about the numerical. Okay, about the numerical experiments, we have 3 scenarios with different urban expansion, and we see in the picture of the right in the bottom that the surface fluxes change drastically, principally the sensible heat flux and the ground flux increase severity, and the latent heat flux reduce for the reduce of vegetation in the land cover land use projection. And about the heat storage in the PBL, and that is the atmospheric boundary layer, when we increase the expansion of the urbanization, also get more heating inside the PBL, that it corresponds with the process of intensification of the heat wave. Is the same? Okay. Now, as a result, we find that in the water type 1, water type 2, when it's a centered anticyclonic system in Mexico Valley, both phenomenon, urban heat island and heat waves, has a moderate intensity. And when in conditions where the throat it's in the middle of the territory of Mexico City, this produce cloudy conditions, strong winds, and also this produce a weak urban heat island and heat wave condition. But in the case where the anticyclonic system is centered specifically over the region, Mexico Basin, there are a strong intensity or intensification in the urban heat island and the heat waves. Okay,
I think we have to hard scold. We have to wrap up. Sorry, we are out of time.
I don't have more time.
No. We are out of time. We don't have any more. We have to move on. I'm sorry.
Okay.
We don't see any questions, but if you have questions for Lourdes, please submit them through the chat box on the event Mobi. We proceed with the next speaker, which is Aseem Raj Sharma, who is a research climatologist from BC Ministry of Forest. Aseem, the floor is yours. Aseem, we don't hear you.
You hear me now? Hello?
Yes, but we don't see your screen anymore.
Okay, okay, sorry about that. Let me share my screen. Is it okay now?
Yep, go ahead.
Okay, thank you. So, hello everyone, good morning and everyone, good morning and thank you for being here today. Today I'm going to talk about some of the work we are doing on evaluating different graded data sets and how well they represent the average and extreme climate indices in BC. Let me start by thanking my co-author, Colin Mahoney. I want to mention that this is a work in progress. To set up the context, as all we know, climate conditions govern a multitude of physical and biological processes on which ecosystem and human societies depends. With warming climate, there is substantial change in both mean climate as well as the frequency, intensity, and the characteristics of climate extremes. To understand the changing climate and extremes and their characteristics and context, it is important to have the access to long-term, high-quality climate data. In BC, the spatial coverage of long-term station data is limited. Consequently, graded data emerges alternative for understanding historical and anticipative changes. Various graded data sets exist. However, there is notable gap in the evaluation of these data sets, especially in how well they represent the climate extremes within complex topography of British Columbia. In this context, the overall goal of this project is to evaluate the ability of high spatial resolution graded datasets in representing mean and extreme climate of BC. Specifically, we want to answer how well does graded data correspond with in-situ temperature and precipitation? How does the performance of graded data vary in capturing extreme climate conditions across the ecoprovince of BC? And what is the influence of spatial resolution on the accuracy of graded data in representing mean and extreme? For this, we use the BC as well as its ecoprovinces. An ecoprovince is an area with consistent climate process, relief and regional landform, as well as oceanography. There are a total of 10 ecoprovince regions. One of them in this area, the Marion ecoprovince, is not considered in this analysis. Also, I split the coast and mountain ecoprovince region into north and south, given their higher variability with latitude. To do this analysis, we use daily minimum and maximum temperature and precipitation data. For observation, we use the data from multiple sources, including Environment and Climate Change Canada, BC Hydro, BC's Ministry of Forest, and Ministry of Transport weather stations. You can see in this map the distribution of the stations' data. After different quality control procedures, there were 292 of the stations, out of which 114 stations has temperature data and 258 stations has precipitation data. Most of the stations' data are below 1,000-meter elevations, with not consistent distribution across all the ecoprovince. For example, northern ecoprovince regions have very few stations, while southern part like Georgia depressions and southern interior have more concentrated stations. We evaluated 4 of the commonly used graded data sets, namely CHELSA, the climatology at high resolution for Earth land surface area, as well as daymate. Both of these are 1 kilometer by 1 kilometer, very high spatial resolution data. CELSA data available for 1979 to 2016, but daymate is up to 2023. We use up to 2022. Also, we use multi-source weather or MSWX, which is the operational global database at 9 kilometer by 9 kilometer, and ERA5 land also based on ERA5 using the model from ECMWS. We use commonly used comparison coefficient like mean absolute error, bias, root mean square error, as well as Pearson's correlation and Taylor diagram to show the differences. Also, we use the integrated quadratic distance, which is the statistical measure used to evaluate the similarity between true probability distribution. This is especially important for extreme indices as it ensures that the change in both space shape and location of the distribution are captured. We calculated extreme indices at each stations and then averaged over equivalence as well as for whole base. Now I'll show you some of the preliminary results of this work. This plot here shows daily climatology of the precipitation for different data sets. The black line are observation, red line are CELSA, green line are MSWX, blue line are daymate, and purple line are ERA5 plan. For BC overall, the CELSA has slightly underestimation of the precipitation for daily climatology starting from winter or January 1st all the way up to the end of the year. Similarly, MSWX has also slightly underestimation. However, there exists a regional variability among eco-provinces. For example, the mountainous subboreal eco-province region where CELSA has a very a large difference in underestimations. But in the lower elevation regions like Georgia depressions, the daily climatology is more consistent. This plot here now shows the daily climatology of daily maximum temperature. I want to mention here that similar pattern were observed for minimum temperature with slightly higher variations, however, especially for lower temperature. For overall BC, ERA5 land is slightly lower, but other regions, especially in mountain region, there is higher variability, and more valley or flat eco-province region, there is more consistent. Summer temperatures are more precisely represented across all the data sets. The temperature is very well captured, especially in the plain area like taiga and boreal plains of the north. While there is much variability, especially in winter months along the eco-province regions which are adjacent to coastal, like coastal and oceanic mountains for south and north. ERA5 land and MSWX are slightly underestimate the maximum temperature along mountainous eco-provinces, likely because of their relatively closer resolution than the CELSA and daymate. Now, in this plot here, we see this Taylor diagram here, we see how the standard deviation normalized correlation as well as standard deviation correlation and root mean square are compared among all the eco-province regions and BC. The correlation, root mean square error, and standard deviation are plotted for all eco-province regions. Anything close to this red line, like red curved line, and this point represent the better agreement with the observation. The daymate is better for whole BC with higher correlation and lower root mean square error. It's even better for eco-province regions of Georgia depression and coastal mountain southern region where there is the high station density. ERA5 line also has higher correlation and lower ST for overall BC and some of the eco-province region. However, for other eco-province region, there is variation. For example, like Coast Mountain North or Boreal Plains has lower values. This plot here, now again for the term maximum temperature, again the same parameters like ST, RMSE, and correlation. For temperature, it is more closer to observation than precipitation. Thus, graded data are more accurately represent temperature than precipitation as expected, given the precipitation has more heterogeneous than temperature, both in space and time. Okay, now this plot here indicates normalized IQT as well as root mean square error values calculated against observation for daily minimum, maximum temperature, and precipitation. As expected, daymate seems fairly more precise and accurate in representing temperature and precipitation, followed by CELSA, especially for precipitation, because of their high resolution. However, this is not consistently true across all the eco-provinces. In fact, MSWX has lower IQT for maximum temperature in the plain region of Northeast BC, while MSWX is better in representing precipitation in some of the eco-provinces. From this and previous plots, we can see that ERA5 has relatively high precision, but lowest accuracy compared to other datasets. The higher accuracy in the daymate, especially in the province with higher station density and lower elevations like GED or Georgia Depression are likely due to the use of large number of stations during their assimilation and topographic regression at very high spatial resolution. In case of Chalsa, which is good in capturing precipitation, especially on mountainous provinces, it considers wind field, exposure, and boundary layer height in its assimilation, and likely that's resulted in higher accuracy of precipitation. MSWX datasets incorporate satellite and also station-based data and reanalysis to obtain those numbers. Okay, now this one plot here shows the summary of how different datasets compare for extreme indices. We calculate more than 60 climate extreme indices for each of those stations using daily temperature, minimum, maximum temperature, and precipitation. That include 27 of the core indices defined by the expert team on climate change and dissection indices and other sectoral indices. We calculated IQT and other comparison coefficients for each of those indices. Given the large number of these indices, we broadly divide the indices into 4 main categories: cold-related, drought-related, heat-related, and precipitation-related indices. Looking at this comparison coefficient, IQT norm, RMSE, you can see that daymate and Chalsa are better represent the drought-related indices for BC and most of the provinces. Daymate and ERA5 are better in representing heat-related indices, while ERA5 land and daymate are better in cold-related indices. MSWX and Chalsa are better in precipitation-related indices. So for extreme indices, the resolution of grid data does not make substantial difference, given how in some of the eco-provinces MSWX is or ERA5 is better representing some of the indices than 1 kilometer resolution datasets of daymate and Chalsa. Okay, in summary, this study is not to find the best data, as every data has their own purpose, but it is to evaluate how well different datasets represent the observation in both average climate and extreme climate indices, so that someone who is looking for data, depending on their purpose and region, can choose the data to solve their purpose best. This is even more important in the places like BC, where we have complex topography and heterogeneous microclimate in short span of spatial span. So to summarize my points here, the grid data are more precisely represented, average climate compared to extremes. Higher performance variation occurs among datasets than between eco-province and capturing climate conditions. Different datasets are better at representing different climate indices. Surprisingly, datasets resolution does not substantially impact the representation of mean or extreme climate. We hope this work provides ecologists, foresters, and other grid data users an option to carefully select the data, depending on region and process. Thank you, and I'm happy to take any of the questions you may have. Thank you.
Thank you, Aseem. Thank you for being on time too. I don't see any questions in Q&A just yet, but while we're waiting on them, I was wondering, did you consider Kappa data set for precipitation? That's also very highly resolved data set.
Not it. I should consider that, but at the first we are trying to calculate climate extremes, and for that purpose we needed is daily temperature, precipitation, minimum and maximum temperature and precipitation, and we try to have those data sets which have all these 3 parameters, but that's a good point to include. I think it has only precipitation and not temperature data at first place. That's why it was not included in the first round of analysis.
Thank you. And we have a question from the chat. Aseem, did you do any analysis by elevation band?
Yes, as I mentioned, it's a work in progress, and I am working on like some of the lapse rate correction and elevation band one, but the results are not ready yet. Hopefully, we'll deploy it into a manuscript where that information will be included. Like we have stratified stations above 2000, below 2000, as you can see in this map in the slides 5. I think we can go, and I'm in process. So as I mentioned in the beginning, it's a work in progress. That's another part we are working on these different elevation bands, how well they represented both temperature lapse rate and extreme indices.
Great, thank you so much, Aseem. We have to move forward in the interest of time. So
Okay, thank you.
The next speaker is Victoria Slonosky, and who is the Chief Scientific Officer at Open Data Rescue. Victoria, go ahead. You have 12 minutes.
Thank you. So I hope you can see and hear me. And I will just try to start the presenter. There we go. Can you see it?
We still see the upcoming slides. So
sorry. Play from start. There we go. Here we go.
Yay! Great. Thank you.
All right. We've got there. Okay, well, thank you. And thank you to Lisa and Nathan for organizing this session. It's been great listening to all the presentations over the last few days. I'm going to go on a slightly different track, I guess, because we're going to look at social data as well as meteorological data in this talk. So we're looking at the challenge of using newspapers as digital data. So this work was undertaken as part of a research grant funded by the Quebec Research Foundation for the Audace project. And we're quite a team, so there's a number of fellow authors on this. I'm going to break it up into two sections. So the first one, I will be talking about using newspapers as a data source and mostly the challengers and not so many rewards that we've got yet of that. And then I hope to finish up with a quick talk about a case study. So what we're interested in here is what we called breaking the equation. So are socially disruptive events the same thing as extreme weather events? So we're looking at a few different dimensions here. We want to look and see about how vulnerabilities and resiliences change through time, because we have societies change, technology change, and infrastructure change our responses to extreme or disruptive weather events. And we also have responses that change also through time at different levels of organization, whether it's the municipal, the neighborhood, various levels of government. So those change also when we look at different periods in time. So we wanted to try and link using social narratives, which we decided to do using newspapers and weather data. So here we can see some examples of flooding. By coincidence, both of these articles we see at the top were published on May 2nd, one in the 1880s and one over 200 years later, 240 odd years later. So we can see that the flooding especially is something that is a constant scourge in our climate. So our case study, where we're looking at disruptive and or extreme events, how they correlate, is taking place in the St. Lawrence Valley region. And we have two periods. What we're calling historical, we define here as 1880 to 1899, and what we're calling modern, we're defining as 1995 to 2014. So two 20-year periods here. So first challenge is trying to obtain the newspaper reports. So we want to make sure we find sources that cover the relevant periods we're interested in. We want to have papers that have a daily or near daily publication schedule so that we can get as close to the event as possible. They need to have a digital text overlay so that they're actually machine readable. And we wanted to have newspapers that have both sort of local and regional news. So not just, there was a power failure at the local corner store, and not only global things either. We wanted to have that sort of middle range coverage of the newspapers. So these are the sources we found in both English and French for the past and the present. The first challenge we found was that digital text records were not always easily available. And this was mostly due to things like proprietary issues Some of the articles were held by ProQuest, for example, so we needed to negotiate with ProQuest, and others had accessibility issues. Next, once we were able to obtain articles, we found that each different repository had its own format. So we had articles, as I mentioned, for the Montreal Gazette from ProQuest, those were in XML format. The articles we have for the French newspapers for the historical period mostly came from the Bibliothèque and Archives Nationales du Québec, the BNAQ, and those are in text format. And finally, the French modern articles were from Eureka, the database, and those tended to be in PDF format. So we had to devise workflows for each of these different formats of the sources. And then next, this is the biggest challenge of all really, is trying to filter the articles. So two of the repositories, ProQuest and the BNAQ, gave us a complete set of all articles. So every single article published between 1880 and 1899, or in the case of the Gazette, between 1769 and 2010. So we needed to build our own sort of search engines to look at these articles and try to filter the text. And then the platforms that did have search engines, the library databases, were not really easily accessible for bulk downloads. So sometimes there were download limits placed, which meant we could only download a certain amount per week, which meant it took us several months to download everything we wanted to, or there are other limits on the availability of the information. So this is probably the most complex part, and we're not really finished it yet, but we're trying to find out how we can filter the corpora. So we started off by looking at selecting keywords. The first thing we did was look for words from weather reports and national hazards websites, such as those that we can see in the Public Safety of Canada, Environment and Climate Change Canada, in the publication literature, and even in some newspapers that we just happen to be reading. What is the vocabulary that is used when we're talking about weather events or impactful weather events? And then we conducted a first newspaper search, and we looked through a selection of those articles. So we read articles from a first search and looked again, what are the words in common? What are the words that we want to use and refine to make sure that we are trying to select the right articles? And then we looked at word frequencies, and then we reran the search. So this is an iterative process, which, as I said, is not, we have to decide when we finish because it could sort of go on forever. So here is just an example of some of the keywords used. I put them in word cloud just to make a change from graphs. So these are the weather. On the left, you can see the weather keywords we selected, and on the right, you can see things like the impact keywords that came up from our reading of the articles. And then for reasons I'll get to in a few slides, we actually transcribed by hand. We had people read the actual PDF image of the newspaper and transcribed them. So we transcribed by hand a small selection of the articles so that we could compare human transcription with the machine OCR transcription. And just for fun, I looked at the word frequencies of some of these articles that we had transcribed, and these are some of the words that come out from the human transcription articles. So one of the big issues we found when trying to do these searches is that we did not realize quite how much weather and weather events are used as a metaphor or metaphorically. So many of the hits we got were not actually related to weather, both in the past and in the present, and in both languages. We had words like flood of money, flood of sensations, storm of criticism, tempête in French, blizzard in French. There were a lot of times that the keywords, especially the weather keywords that we're looking for, were used in senses that we did not expect and that were not related to what we're looking for. So that was one problem, and that's why we had to do a lot of filtering, and we're still thinking about the filtering. Another problem is to look at the fidelity of the OCR, the machine read or the machine transcribed text to the original text. And this is why we had some people transcribe human transcriptions of the articles a small selection of articles to try and get at this metric. So here we can see the ratio of character differences per word in the transcribed versus the OCR text. And it's not too bad for English, but there's a larger mean and a larger spread for the French words, which are probably related to two things. One are the diacritical marks, which OCR has a lot of trouble with. And the other is possibly that the OCR is not as advanced in French as it is in English, because English is probably used more and is got a larger set of training data. But then I kind of thought, well, what are we trying to look at here? What are we interested in, and what's our sort of problem? And really what I was interested in saying, well, are there articles that are not being selected because the OCR is so bad? So an example that we came up with is food instead of flood, or flood instead of food. Wheat contains the word heat. So if you're looking for heat, you get a lot of wheat hits for wheat and things like that. And here actually it's quite a bit more hopeful, because we found that the number of OCR articles with the keyword detected compared to the number of transcribed articles was reasonably high. So for the historical period, it was 92% in English and 86% in French. For the modern period, all of the articles did detect the keyword we were interested in. And we weren't able to do the modern French because, as I showed before, the modern French were in PDF format, so we didn't have an image format of them. They were all only in digital text. Okay, so I'm just going to explain a little bit what this is to do with actual extremes. I'm going to very, very quickly go through our case study with winter storms. So some of you may remember I presented this several years ago. We were trying to come up with a modified version of the local winter storm scale for Montreal. So here we have an idea of, based on things like temperature, winds, visibility, whether there was a snowstorm or not. So this is just to show you the weather-based data. And then what we want to do is we want to try and compare this weather-based data to how many times we find snowstorm-related keywords in the newspapers. And we have two experiments here. So on the left, there's articles with all articles that have the snowstorm keyword, but with no filtering for words like politics or some of the other things we saw before. The weather-based data. And on the other, we have what we found excluding a list of words like sports and politics and entertainment and things like that. So we go from one extreme to the other with this exclusion. So on the left, we see that we have many, many articles that are not necessarily related to storm. On the right, we see that we have only 5 articles left once we've excluded all the words. So clearly there's room for a middle ground here. So that was the historical, and this is the modern, the same kind of thing that we find. And just again, very quickly, so for the articles that we found with snowstorm results, with the excluded words, so these are the ones from the right, again, I just gave a quick word cloud, and these are the words that come up. And compared to what we saw earlier, it's a little disappointing because we don't see as many words. We do see some words that we want, like weather, water, ice, still, things like that, but we don't see as many. Okay, I'm just about finished. And I just point out that the words processing also takes out all the diacritical marks in French, which is why the French words look a little odd. So some of the reflections here, if anybody is thinking about using digital data, such as newspapers, the material is not always provided in friendly formats. We need considerable resources to clean and process the data. The big takeaway I would say here is automatically generated text cannot be used naively because there are just too many issues in it. But we can still try and detect issues of vulnerability and resilience and changes in the article selections. And with that, I'll wrap up, but I will also hand it over to my colleague, Renee Sieber, who is going to look at more sophisticated methods of analyzing text data. So thank you.
Thank you, Victoria. We have a question from the Q&A chat. if you were to restart the research, would there be a better data source to analyze the newspapers?
That's a really good question. We considered things such as, I'll just stop the share because the next person can get ready. We considered things like insurance reports, but what we really wanted was something where we could compare the two time periods. So there are probably a lot of sources we could use for the modern period, but insurance companies, especially for weather events, were only just getting started in the 1880s, and they were getting started as a result of some of these weather events, especially flooding. So we really wanted to have something that was consistent over time. And I think we'd run into almost all the same problems with data quality in almost every source we use because of the printing and that kind of thing. Although I should point out, we also had issues even with the modern data, which I think my colleague Renee will get into in terms of article selection and things like that.
And we have one more question. I'll read it. Did you notice any change in frequency of certain words used between historical and modern articles?
Yes. So words like verglas and freezing rain, I mean, despite even leaving out 1998 and the storm, it was very rarely used before in the historical period. So whether that's because they didn't have these kinds of events or whether the impact of freezing rain was not the same, so they didn't need to write about it as much. That was something that was quite interesting. The frequency is very different for freezing rain types of events, and transport and infrastructure. I mean, of course they had trains, carriages, boats. There are a lot of boats were being used for transport in the past, and then in the future, well, not the future, sorry, present, future from the past. There's a lot more emphasis on things like electricity. So we have different vulnerabilities because we're not as self-sufficient in, say, heating, for example. So electricity and power are big themes in the present day.
Very interesting. There are a couple more questions, but in the interest of time, we'll continue. So I will invite Victoria to look at the Q&A and answer that. And the next speaker is Renee Sieber, who is a professor at McGill University. Renee?
Can you see me? Can you hear me? And can you see my slides?
Yes to all of those.
Okay, great. Okay, so thanks, Vicky, for a segue. So we're dealing with over 100,000 articles here, and we're looking at ways that artificial intelligence can assist in identifying vulnerabilities and resilience in newspaper reports without applying preconceived ideas about how people coped in the past, cope in the present, and how these coping mechanisms change over time. And we'll also talk about the use of generative pre-trained transformers or GPTs to try to get past the junk, aka the bad optical character recognition or OCR. So Vicky has already explained the case study that we're dealing with two temporal tranches in the late 1800s and in the late 1900s. We looked at a number of newspapers. I'm going to report on the Montreal Gazette, but as you can see, it is a lot of content that we're dealing with, and we're particularly interested in the disruptive weather events, not the extreme weather events, because we believe, supported by the literature, that there's going to be a lot more problems as we endure a lot of weather whiplash, especially in southern Quebec, with temperatures hovering around freezing, for example. This is the whole workflow of the project. Vicky talked primarily about assembling and cleaning the corpora, and I'm interested in the machine learning and AI classifications. So we use a variety of AI, specifically natural language processing or NLP methods. So I'm going to focus. So we've used unsupervised and supervised classifications, and as well as GPTs. So I'm going to be focusing on our use of unsupervised classifications, which very briefly is throw data into a bucket and just see what percolates out, which is very different from Vicky's method, where she actually questions whether or not we can, how much we can trust this throw the data in the bucket. And we will take as a given whatever we see as emergent categorizations. Tomorrow, I'm going to be talking primarily about supervised classification on my Environment Canada and climate change grant. But I'm also going to be talking here about generative pre-trained transformers. So unsupervised classification, we performed this on the historical data and also the modern data. We predominantly used LDA, or latent Dirichlet allocation, to see what topics bubbled up out of our newspaper analysis. In terms of historical, this is the common visualization program for LDA called LDA Viz. So in the word clusters, we're looking for concepts related to vulnerability and resilience that show up or can be computationally boosted to be revealed, and whether or not these concepts change over time, whether vulnerabilities, as Vicky mentioned, in the past differ from what's happening in the modern period. And as you will see here, some topics that show up are things like, or some words that show up in topic number 10, like storm, train, steamer, wind, and blow, which is talking about the impacts of weather on vehicles in the historical period. This is in historical English, as opposed to the present, where, and I'm looking at topic number 5 here, where we see game, Canadians, ice, and last night, and that's one of the problems, past or present, that you can get certain topics that dwarf other topics. And ice, if you're looking for ice, you're going to get hot references to hockey, and that's why you have to start looking beyond the primary topics to topics deeper in the clustering. And one of the reasons we're also interested in disruptive weather events as opposed to extreme weather events is that they're not always bad for impacts, say, on recreation. And that's indeed what makes winter weather different from other impacts of climate change. That we may have opportunities, more opportunities for hockey or less opportunities for hockey, considering whether or not we have to worry about the ice rinks are freezing during winter. Vicky mentioned that AI hopefully can help us manage large volumes of text, but there's a lot of metaphoric noise. And here are some more metaphors that can swamp any automated analysis of this content. We also used an automatic labeling package called Atlas Nomic to look at a spatial distribution, not geographic, but a spatial distribution of dominant words and their adjacencies to other content concepts. And this is working with the entirety of our data set in historical, around 42,000 articles or pages, and present 78,000 articles. Okay, this just is, don't freak out. This gives you a sense of the quantity of articles we're dealing with. Each one of those points is linked to an article, which you probably can't read on the left-hand side, but it gives you a sense of the automatic labeling that is done when you use LDA. In the previous example, that has to be labeled by hand. And here's a zoomed in version. And in this package, it also, there are more labels the more you zoom generate, and you get some sense of some weather-related disruptive or extreme weather event clustering of terms. Here's an example from the late 1990s where you see impacts on winter tires and tire pressure. So preparing your car for the winter, but also preparing your plants in the lower right for winter weather and how that is going to change over time. And also whether we can learn from the past how they prepared for winter. Here's an example of vulnerabilities to the supply chain, but also in the lower left, that is snow is not always a bad thing. And this also gives you some sense of the challenges in working with this content, because it can be very noisy. It can be very dirty, even after you spend all of that pre-processing time and you do all that filtering to achieve a derived corpus of pertinent articles that have the terms we're looking for in them. So we then shifted to transformers. Why? Because we're looking for ways to increase our ability to eliminate noise. And I want to show you an example of an article that gives you that clearly shows the noise, to infer gaps, quote marks, spaces in the text, to fill in words because it's predicting the next word or the next part of the sentence, dependencies, but also to hopefully eliminate some bias where we're looking for things that are not related to hockey, for example, and also scenario planning, which is the core of our exploration of vulnerabilities and resilience. Here is the noise. And this is very messy data. You can't even necessarily submit that entire article to a GPT. You often have to chunk it up. So you may have many chunks that are just complete noise, but you can still get some results. So does the following text, the previous text, suggest effects of weather? And here's where the inference can help us, that even infers across FL space OOD. It says that must be flood. So it says, yes, there are impacts on agriculture, on the private sector, in terms of drawback to various aspects of business, and influencing the supply of wheat. So here are some of the preliminary results that we found. We did find some constants across tranches in terms of impacts on agriculture and on energy, but also complaints about potholes and road conditions. Variability, obviously we don't have the ice bridges that we used to have. And we don't have to worry about when we change from carriage wheels to carriage rails. But now we're dealing with damages to the ski industry and the use of artificial snow. unpredictability. In the 1880s, there were a lot of floods. And now there might be some more predictability in the events, at least in the 1990s, but also resilience could be seen in our new normals, how we respond to this unpredictability and build infrastructure to protect us against that.
A minute?
And this is my last slide. That the next steps for us is something called retrieval augmented generation, to create our own GPTs trained on our data sets. And the reason why this is so incredibly complicated is that we get used to ChatGPT being cheap or free. Once you move to the application programming interface, it can be very, very expensive, particularly when you have token limits and you have to process everything one chunk, and articles can have up to 5 chunks at a time, and you have to store them in the cloud and pay for the cloud. And that is it. Thanks.
Thank you so much, Renee. That was so interesting. I was so interested that I even forgot to give you a cue earlier. I don't see any questions just yet. Yeah, like I was wondering how so like you were showing these parts when there are like some LOO space D like or something like this. So what's the percentage of these mistakes you see like during during your processing?
Vicky can answer that. One of the huge challenges of working with automation is you don't see those minute errors that can add up. Therefore, I have to rely on someone else to produce the box plot for me. But so Aseem asked a question in our Zoom chat.
I think that was a the question for Victoria.
Okay.
So yeah, I don't see any.
No, I was just gonna say, yeah, I'm just trying to read it. Well, it could be for both of us if you wanted to talk about it too, Renee. Yeah.
Well, our goal in looking at this is to get a sense through the lens of newspapers what the public is concerned about, because journalists are likely going to write about what the public is concerned about, and and also how we communicate that. So if people are more concerned about certain aspects of the electrical grid, maybe we can tune some of our communication strategy to more comments about that. And it's always a challenge for Environment Canada, as how far does it step outside of computational analysis of the atmosphere to how do we engage with the public?
And I would say it can also show us because we think that what we have is the only thing. When we look at the past, for example, we can see, oh, well, before there was a power grid, people had their personal stock of food. And that's the kind of thing that we have in public messaging. We say, be prepared, the government is saying things like be prepared, have 3 days worth of food and water and things like that, which was the norm in the past. And maybe also to make sure we have backup systems of heat and transport and things like that. One of the things that worries me with electrification is that if anything goes wrong, we're in a lot of trouble. So resiliency is also about diversity, I think. And that can be part of the policy planning.
Thank you so much for that answer. So we are going back to Victoria, whose presentation is already on the screen. So go ahead, Victoria.
Thank you. So I'm back with a different hat on now, but it's the same kind of idea with past weather observations. So here I am going to talk about a project that I've been working on with various colleagues, including Rachel Black, for the last 3 years, which is the development of a data set of historical Canadian weather and how we can use that to look at climate variability and climate extremes in the past. So here I'm just going to talk about the scope of the project, which is the title of which is Transcribing Historical Canadian Data, the Smithsonian Records. So it was conceived by Xiaolan Wang and administered by Vincent Chang at Environment and Climate Change Canada. So a huge shout out and thank you to them for the support of this project. So initially, as you can see, it started with the Smithsonian Records. The Smithsonian, there was a volunteer weather observing program, especially over the 1850s to 1870s across North America, which was organized by the Smithsonian. And many Canadian observers participated in this and sent their observations to the Smithsonian, which were then held by various archives in the US. So we expanded this in the last year of our project. It was a 3-year project to look also at other overseas archives, such as the data that's being held in the UK Met Office archives and library. And this project was undertaken by Open Data Rescue, which is a not-for-profit organization we set up in 2020 to try and locate, find, transcribe, and curate, keep a lot of this heritage data that we have for environment and climate. So let me see if I can get this, oops. Yeah, okay. So I think it plays automatically. Here's the distribution of the stations in 20-year chunks. You can see that, if we might have been able to see before, there were a few stations in the 1700s. We have a lot of stations in the 1850s to 1860s, and then we kind of go up to 1875. So this gives an idea of the geographical extent of where we have information. I've talked about this before in CMOS, so I'm only going to go over it very, very quickly. We have a transcription process, which is undertaken by a web app. So our transcribers sign into the web app, open up a page. A page is a digital image of one of the weather observing records that we've collected and digitized, et cetera. And we have what we call a transcription environment, which is that little box you see in the front. And what this does is it chunks up the data into small pieces. So we have usually about 3 or 4 and sometimes up to 5 pieces of information that we ask people to type in directly from the page into this box. And from there, it goes into our database directly. So we don't have spreadsheets and we don't have intermediate issues with the data. So there are some of the things that we look for in trying to clean the data, or our sort of data processing workflow, if you like, is to look for things like text input errors, first of all, things like putting O instead of 0, putting in 2 decimals by mistake, et cetera. Then we look for, we try to figure out how to code for missing, unrecordable, or illegible entries. Now, this is very important because for things like precipitation, cloud, wind, to have no data is not the same thing as saying the data is missing. Because if there was no rain, then you have a blank, but it doesn't mean that the data wasn't, nothing, it doesn't mean that the data is missing, it means that there was no rain. So it's actually a positive piece of information, even though the field is empty. And then we need to figure out how to convert the data, especially into modern units. For things like temperature, that's pretty easy, but things like wind force that are recorded in pounds per square inch, it's a little bit trickier. And then we check for outliers, and that's what I'm going to show in the next couple of slides. So for each of the fields that are continuous, we run the data through a program which calculates the 20-day, well, it depends on the field. It could be anything between 10 to 20 days, running average. And what this, and we also calculate the plus and minus 5 sigma values. And any values, especially single values that are beyond the 5 sigma value, is flagged, and we can see it either in graphical form, or we also have a list of values that we can look at to be investigated for potential errors. So this, because the Canadian climate is so very variable, we can't really put fixed boundaries. This allows us to pick out errors without having to have a fixed boundary for temperature or pressure and so on. So another way to try and look for outliers or values that we think are just wrong is comparative. Because we're typing in so much data and so many related pieces of information, we can, for example, compare different fields to each other. So here's a graph from May to December of thermometer values that are related to the thermometer in Quebec City. So we have the air temperature mean. These are daily. We actually have air temperature every 2 or 3 hours. Oh, no, sorry, 2 or 3 or sometimes 4 observations per day. So we have sub-daily data, but here, because we're looking at other daily information, we're looking at the daily mean air temperature, which, as you expect, should be in the middle of the graph. And then we expect, for example, maximum temperature to be higher than the daily mean, minimum temperature to be lower. But we also expect the black bulb radiation thermometer to be higher than the maximum temperature and the grass minimum thermometer to be lower than the minimum. So we have a lot of ways of sort of cross-checking information. So here is, we have over 1 million pieces of information in here. And here I'm just sort of breaking it up to give an overview of our data set by variable type. So the most common variable we have is air temperature, including all the ones I showed earlier, such as minimum temperature, maximum temperature, as well as just the hourly temperature. We also have a lot of information on clouds, which is really good because clouds are something that we're kind of interested in for the climate system. And finally, I have here velocity and direction, because as well as wind velocity and wind direction, there are also lots of recordings of cloud velocity and cloud direction, which give us an idea as to the upper air conditions. And then we have barometer, wet bulb temperature, water vapor, so other humidity related variables. And precipitation, as I mentioned earlier, is quite low because we have a lot of times when it's not raining. So we don't have as many positive observations of precipitation. And here, so here we're sort of moving into analyzing the data as opposed to just collecting and cleaning it and processing it. Here we're looking at the distributions to see, well, does it look okay? Especially considering these are observations taken over 150 years ago. So we're mostly pretty pleased with these. We can see that we seem to have caught most of the outliers, and most of the stations seem to make sense in terms of the distribution. The air temperatures mostly for stations in Quebec, Little Whale River, for example, being further north, and Stanbridge being south, and St. Anne being on the St. Lawrence estuary. And same thing for barometric pressure. This is station pressure, so we can see stations that are at higher elevation have lower values. We can also see Quebec City is quite variable, which makes sense also because it's in the middle of a storm track. So then how can we put all these together to kind of look at the weather and what the weather was doing in the past in these kind of times? So we're trying with various different coding packages to see how we can put all this together. Here's an attempt to look at the weather. This is just a date picked at random, February 15th, 1862. And here, so we have the wind direction. We're sort of have the wind force, but as I mentioned, wind force is kind of tricky, so I'm not super relying on that at the moment. But we also have temperature and the colors and cloud cover. I don't know if you can see this, but some of the circles are 3/4 filled or 1/4 filled or half filled. And that's to show us what the cloud cover was like. So we can have a sort of synoptic idea of what was happening at a given time over the country. And then this is a change for our extreme events here. This is possibly one of the coldest spells I found in the records for Southern Canada, which is January 6th to 14th, 1859. And here we're trying to plot them to see how the cold spell sweeps west to east across the country, starting in Red River, which is now Winnipeg, and ending in St. John's. Although by St. John's, it's kind of petered out, but we can see how it affects Kingston, Montreal, Quebec, and the eastern stations. So these have some of the coldest temperatures recorded in the southern Quebec and Ontario regions with temperatures below -40 for when the peak of the cold wave came through. And because we heard so much about fire and smoke and forest fires, especially yesterday, I thought it would be interesting. I showed a version of this last year, but here I've been able to add in the extra data we had for the year and make it a little bit more sophisticated. So I thought it'd be interesting to show the reports of fire and smoke across the country. So this is not for a particular day. This is just how many times in any particular location there is a report of fire and smoke. And we can, there's no data for BC or, well, the Western Canada, just because we have no stations there. Doesn't mean there are no forest fires, that this is a limitation. We can only report what we have. But yes, it's interesting. We see it up north. We see reports of fire, and that's really interesting because those records are very short. The records at York Factory and Red River, here's York Factory, here's Red River, those are longer, and we can see actually there are quite a number of reports of fire and smoke there. And it goes all the way across from James Bay, even to St. John's. So yeah, this can help us maybe get an idea of the variability of the climate and help us better understand the nature of extreme events.
1 minute.
Okay, perfect. I think it's my second to last slide. So another thing we can do is there are so the people all around the world are doing this kind of thing and transcribing and processing historical data. And then this goes as the basic uptake data to reanalysis products, like the 20th century reanalysis, which is no longer 20th century and now goes from 1806 to, I think, 2015. So there are thoughts about whether that should update the name, but so far it's too much of a brand, I think. And what we can do is we can sort of compare the observational data with the reanalysis product and see where there are biases and where we need more information to try and improve the reanalysis product. So that's a quick overview of this project. We want to make sure this data goes into an open data repository, which is partly why we're doing some of these analyses, to make sure we don't have ridiculous information somewhere because of a weird transformation. And so we hope to do that in the next couple of months and to document this in the literature. And especially a big thank you to all the transcribers who have, between them, typed in over 1 million pieces of information. So thank you.
Thank you so much, Victoria. That was very interesting. And while we wait for the questions in the Q&A, I actually was wondering, like, you said like you were looking like at the event, so like in case the event exceeds like 5 sigma, but 5 sigma is a relatively wide margin. So like even 2021 heat wave, like I think it was 4.5 sigma, and it's like was so outstanding. So yeah. Why 5? Yeah.
Okay, that's not for an event. That's to look for what we call an outlier in the data processing. So if somebody wrote 73 instead of 37, that's the kind of thing we're trying to find. So we're trying to find basically typing mistakes, or sometimes the mistakes are in with the observer. The observer wrote down 73 instead of 37. But that's for that part with the 5 sigma. So we want to balance it between saying, okay, if it's something like somebody recorded -100 instead of -10.0, well, we want to find that. But we also don't want to be going through 1 million observations because we said, okay, well, you know, -35, let's have -35 as our cutoff. And of course, in the north, we have thousands of observations of -35. So that's why we're trying to have this running mean and the 5 sigma, because 3 sigma gave us too many false positives. So we're just trying to find various ways of making sure the data are reliable. So this is one screen. The other screen, as I mentioned, was comparing variables. So sometimes we have the mean temperature written, and sometimes we have it, the 3 variables. So we can calculate our own mean of the 3 variables and compare it to the transcribed mean. And we also have, I didn't mention this, but we have things like dry bulb thermometer. So we can see what the difference is between the open air and the dry bulb, because that should be quite small. So different, yeah. So it wasn't to look for an extreme event, it was to look for bad data, I guess.
Yeah. Great, thank you. And we have a question. Do multiple people transcribe the same entries to avoid error in that process?
No, and we've actually been looking at studying this for quite a bit. So that is a sort of typical transcription or citizen science way of looking at things. But we found in general, there's less than one error per page. So if we were to have everybody transcribing if we were to have every page transcribed 3 times, for us, that would be 3 times as much time and effort. And you don't necessarily catch the issues, because the issue, as I said before, could actually be with the original transcription. It could be everyone thinks the 5 is a 7. One of the things we found a lot is 51 and 57, because there's a dash across the 5. If it's not close enough to the 5, people think it's associated with a 1, and they think it's a 57. So if everybody does that, we won't find the error. And we found the error rate was very low. So that's why we're investing in the programming to find the errors rather than in the multiple transcription, because if we pay our transcribers as of this project, or if we use citizen science, it's still effort that we can put into transcribing other data sets. So
great, thank you so much.
Thank you.
We have our last presentation from Melissa MacDonald, who's a program meteorologist at Environment and Climate Change Canada. Hey, Melissa, go ahead.
All right. Share my screen. Oh, just a second. Share. All right.
It's still not full screen, but
Oh, yeah,
yeah,
just a
we
second.
can.
No, it will be. All right.
Great, thank you. Go
All
ahead.
right. Well, thank you very much. First, I would like to begin by acknowledging that I am joining you from Mi'kma'ki, the ancestral territory of the Mi'kmaq people. And so, yeah, I'm a program meteorologist with our Health and Air Quality Forecast Services program. My main role is our extreme temperature lead. And I'm going to talk about understanding extreme weather events in the context of climate change. And I'm going to do this through analysis of our public alert data at the Meteorological Service of Canada, looking at maps. And I have to be honest, I put way too much into my presentation, so I'm rushing to try and finish it. So hopefully I'll make it through. All right. Oh yeah, so this project started for me because I was trying to find a way to support our heat public health partners with their post-season reviews. I was tracking by hand any heat-related weather alerts, and then summarizing them into tables, and then eventually I decided to summarize them into maps for presentation. So this is an example of one of the first maps I made for 2017, showing the number of days we had heat warnings in effect. Then this became more of like a visual reporting tool that our senior management got really interested in and started being used in year-end presentations. And then I expanded it to look at our air quality alerts and our extreme cold alerts that fall under our health and air quality program. And then fast forward 2022, I was requested to look at like all weather alert types. And there was quite an increasing demand for this kind of information from our partners and the public itself, just thinking about alerts in the context of climate change. So just, I guess, a little bit overview of this idea about our MSC alerts. For first thing is we don't have an actual weather alert data space. It doesn't exist. So this was definitely a difficulty. We do have our Archeon database. It stores our observational and bulletin type data. So all forecast bulletins, all alert bulletins, but they're all stored as text bulletins. So you have to be able to parse the text to get the information. So using some of the data that had been pulled out of that by our performance management program for verification of alerts, and then Python scripts and regional lookup files that had been developed by my co-op students, we started being able to calculate the number of days per fiscal year that an alert was in effect. So some notes about my alert maps. So of course there was data limitations. My original abstract stated that we'd look at data from back to 2012, but that wasn't possible because of how the alert data was stored. They were only stored as like one entry, not necessarily the start and end date of the alert. And then also the alert maps are done by fiscal year for the reporting purposes. But then as I move forward, I thought of this as being a bonus because then we weren't dividing the winter season. We can look at snowfall, extreme cold across the whole season. All the data is represented by calendar day in universal time. This is a problem. I'd like to see it in local. So I think I'm going to work to adjust the data for that aspect. And then it's all correlated by the public forecast region. So each of these little squares you can see on my tiny maps here are our public standard forecast regions. They can be divided smaller into what we call meso regions, but for this purpose, I'm correlating everything to the standard region. And that's where how we issue our alerts and forecasts. And then note the gray and white areas. We do have dots up here in the Arctic, but the gray and white areas are not, currently we don't issue forecasts or alerts for those areas. They're very low populated areas, if populated at all. So my first set of maps is only 6. This is our heat maps. And the reason there's 6 is because of one of the limitations of looking at this data, and that's that we've changed the heat warning criteria over the past 8 years to be evidence-based. And then with that too, these maps are a little different because they're actually looking at the calendar day locally because I was using those tables I created by hand. They also are thinking of only impacted days. So one problem with some of looking at the alerts is the warnings are often issued before the event happens. And in the case of heat warnings, we actually have a rule that says the heat warning should be issued 24 hours in advance of the event. And that's to allow for our partners to put in place their heat alert response plans, but also in case the public wants to change their plans in association with the alert. And then on top of that, so I was able to remove that day when counting the number of days. And then I also was able to remove the day if the warning ended, see in the wee hours of the morning, because that's not really impact in terms of response plans still continuing. And the public's, of course, going to see more relief from heat. So that's definitely a bonus, I think, in this case, because I can present them as an impact for sure. In terms of a trend with the heat warnings, we're only looking at 6 maps, so I can't really say. We can highlight, of course, the 2021 summer, which is when we did have the heat dome event in Western Canada, though the numbers are higher in our Alberta than they are in BC in this case, because of course Alberta had other events throughout the season. I will highlight another limitation too, is that this is only what the forecaster expects to see. So in the case of our heat warnings, the forecaster is asked to err on the side of caution. And therefore, the criteria for heat warnings includes an overnight low, and the overnight low is harder to forecast and can be much more variable across the region. Therefore, the forecaster may err on the side of caution and keep the warning going longer than it needs to be, and doesn't necessarily represent exactly what would have happened over time. The next panel, 6 panels of maps. And I should mention too that they do go chronologically from east to west and then top to bottom. Show our air quality alerts. Air quality alerts, for the most part in Canada, are related to wildfire events. So you can look at it as considering wildfire events as well. And you can see that we do know in the context of climate change that we have seen an increasing amount of wildfire events and air quality issues related to wildfire, but we're only looking at 6 years. And when we talk about that increase really started around the 2017-18, 2018-19 period. But we can definitely see a trend in the big wildfire season of 2023-24, or 2023 in this case for the wildfire season. I'll also highlight like a correlation that I noted with these is that 2018-19 and 2023-24 are known as being El Nino summers, and El Nino is associated with warmer temperatures and less precipitation, and especially in Western Canada, which tended to be our extreme wildfire seasons. So just another note, a little bit more about the idea of looking at the alert data in terms as a climate change indicator. This has come about because of increasing requests for alert data, most of those to support research, generally in the climate change context, but also a lot related to decision makers requiring in preparation for climate change resilience and emergency response planning. So that's led me to talk a lot about those limitations when providing this kind of data to our partners and inquirers. One of the biggest limitations comes from the assumption that when asking for alert data, that it is going to represent the rarity of a certain weather event. And for almost all of our alerts, we have a single threshold that's crossed, and therefore you don't necessarily have an idea of the severity after you've crossed the threshold. And that's not necessarily represented in just the events themselves, especially when thinking about things like heat and cold, when you can have so many days throughout the season that can fall under an alert, yet not be the most extreme of those events. Other problems could be changes in the alert criteria, like I showed or discussed it with heat warnings. And then, of course, we learn from advancing science, our partner consultations about the impacts, and that adjusts the forecaster process over time as well, their workflow. And then also one thing that I did forget to mention, I'm just going to jump back to this slide, how the forecasters are told to deal with the alert. So you can see in these slides in Atlantic Canada that we do see air quality events in earlier years up before 2023. But in Atlantic Canada, the reason for those is that we were issuing special air quality statements just to talk about smoke aloft, or yes, that is smoke from out west that you can kind of smell or see, but it was not necessarily reaching the threshold that we've now set of an AQHI of 7 or more as being when an air quality alert should be issued. And so as the forecast practices change, that really affects what kind of alert information you're seeing. And then the biggest one of all, of course, is the fact that it's such a limited data set. It's only 10 years of data. Can that really, show a climate change trend? Well, I guess I'm going to try and show you so. So here's my 10-panel map format, starting with extreme cold. And in the case of these maps, they all go the same left to right and top to bottom. I know it's really hard to see the scale, but the color scale across all maps is the same. In terms of extreme cold, I really anticipated seeing a trend. I think that we talk all the time about seeing not as cold winters, less snow. However, I did not see a trend when you look across the board at these maps. I can't tell you that I feel that from 2014-15 up to 2023-24 that we've seen a decrease. You compare only those two maps, perhaps so. What I can highlight, though, is the 2 years that we had a mild La Nina. So that was 2021-22, where you see really intense blue coloring. And I actually had to raise the scale to 65 days as compared to 60 in this map. So that is the one exception. And then in 2022-23, which you don't necessarily see across the country in the same way, but Atlantic Canada saw extreme cold warnings across the entire area, and that was never, ever seen before. And so that's cold reaching the south more. And my next set of maps is snowfall. It does not include snowsquall, blizzard, or winter storm, which all would include snow as well. However, I will highlight, I didn't necessarily see a trend either, but I can point to the years that were El Nino when you expect to see reduced precipitation. So the first two here, 2014-15, no, not so much, but then 2018-19, and then also in 2019, or the most recent year, 2023-24, and we do see a bit less precipitation through those. Rainfall warnings, similar to snowfall. I didn't necessarily see a trend specifically. I do think I see a trend in Atlantic Canada in increasing days under rainfall warnings, but I will highlight too, Nova Scotia sees a big one here, and I think it was the sensitivity to the extreme rainfall event last year where they started issuing more rainfall warnings than before. Hard to say. This one, I feel like I really see a trend. So this is convective warnings. I don't see a trend across the entire country. Convective warnings include severe thunderstorm and tornado warnings. But I do see a trend, an increasing trend in Eastern Canada, Ontario, and Quebec over the last 4 panels down below. Is it because of more convective warnings needed, or is it a shift in forecaster practices? That's another question. And then my final set, my final set is synoptic warnings, which I really anticipated seeing a trend because we hear about, climate change associated with more extreme events. And I think that was the association with convective events. But with synoptic warnings, I don't see that trend. And I think the problem here is that I have heat and extreme cold mixed in. So for example, the synoptic or 2021-22 map is almost the same as the extreme cold map. So this is my final slide. In summary, I don't think that all MSC alert data, if any, can actually be used at this point in time to represent climate change, and a larger time frame is definitely needed. Rarity or acknowledgement of rarity does not exist in looking at this data. I always point people to media in particular, or also to the top 10 weather stories, though I caveat the top 10 weather stories of thinking about it's supposed to be for all of Canada. So if all the rare events happened in the West, we're not going to list only them, or extreme events. And then moving forward, MSC is moving to impact-based tiered alerting with associated messaging, and we are starting to collect and save all alert data for her future database, and it also includes the forecaster input into deciding the alert decisions. So I think this is going to be really beneficial in the future, and that given more time, we should be able to demonstrate climate patterns at least, if not climate change, looking at the alert data.
Thank you so much. Yeah, the high school, the database would be so good. I remember I had to contact you when, like, after 2021 heat wave, to try to look for the information. Yeah, it would be great. So we have a question from the Q&A. If we see more alerts, will we see greater granularity at the higher end of the legend, as well as the new normal of degraded air quality?
Oh, that's a great question. Maybe can you repeat it just once more for me? And I'm going to go to those maps so that I can talk about them.
Sounds good. If we see more alerts, will we see greater granularity at the higher end of the legend, as well as the new normal of degraded air quality?
I would say yes, if needed. I didn't highlight, of course, that I had to, I had to create 135 to 150. That's what this one is for 2023. It was like another point I wanted to sort of highlight on. However, that greater granularity only exists within just a few forecast regions, or the higher quantities only exist within a few forecast regions. So I think the reason I have such granularity for the other regions is so that we can see the distribution more so between all forecast regions. But it's definitely something that I'll consider as the numbers increase up there, but I don't know if you would see a big difference because there's only one region falling under the 135 to 150 days category. So yeah.
We have a few more questions. One of them is, could we retroactively issue alerts for the past using the past data?
Actually, that's a great question. So in terms of heat warnings, because we've developed new evidence-based heat warning criteria, I have recently undergone a project with the support of co-op students to look at if we applied our heat warning criteria historically over time, as we do now, what kind of information would we receive, and how would I be able to, I'm going to plan to represent the maps in a similar way and be able to compare the years. So yes, I think it can be done looking at just the weather data, but I think that touches on one of the points I made about looking at the maps here for Alberta, for example, is the fact that it's really different to look at historical actually observational data compared to how the forecasters saw the event before it actually unfolded.
Thank you. We have two more questions. One of them is data available for more meteorological scale research? For example, a list of every thunderstorm warning day for Ottawa. Sorry, I have to read it again. Is data available for more meteorological scale research? For example, a list of every thunderstorm warning day for Ottawa.
I ran forward here so that you have my email address. So I have been providing this kind of data. That's really how I've gotten into it to so many partners across the MSC overall that, I'm saying it's available. And if I've already captured it, then it's easy to provide. If it requires work, it may be a different story, but don't hesitate to reach out.
And the last one, do you have an idea of how often the alerts based on the forecast verified?
Oh, wow. I think that varies. At this point in time, no, I can't. I can give you that indication based on heat warnings for the most part, because I've really dived into that information, considering we've adjusted the criteria and we have so many partners closely related to it. But no, I have not had the time at Anyway to look at verification versus what I'm providing in terms of alerts. I think that it could be done to a certain extent, but I think it would depend on the alert type and the data that we already have available. And in many cases, I mentioned the performance management, there is verification of alerts being done for forecaster feedback and supporting model advances. However, it's not usually, it's not easy to do because of thinking about representative observations to the alert as well. You know, we have a much larger field of weather than we actually have of direct observation.
Great, thank you so much. Thank you so much, Melissa, as well, all of other speakers from this session. Yeah, this concludes this session. Thank you so much, everyone, for participating and listening. There will be the recording available on Eventmobi platform, so if you missed the presentation, please go ahead and check it out. And yeah, with that, we will wrap up. Thank you.